Okay, yeah, I'm Rob. I'm a senior data scientist at MaxPoint. I'm going to talk today about Bayesian logistic regression and a little Python package that we threw together in open source because we didn't find capabilities in standard Python packages out there to actually do this. So this package is open source, BSD 3-clause license. You can download it, you can do whatever you want with it. It comes with no implied warranty, etc. And so what this talk is going to be about, it's going to, because it's the end of the afternoon and you're all falling asleep, I'm going to wake you up with a little bit of math, and then describe basically what Bayesian logistic regression is, how it relates to L2 regularized regression, and so on. In particular, then we're going to discuss this Python package that we put together. And essentially what it does, it allows you to assume priors on your fitted parameters in logistic regression that do not have zero mean, as they would in L1 or L2 regularization, and allows you to do recursive updating the logistic regression model as new information comes in. We'll also discuss another aspect of the package that has to do with variable selection for sparse models. So this doesn't use L1 regularization, but there's a neat little trick you can play with p-values to do that as well. So very briefly, what do we do as a company? I'm not going to talk about our company very much, but we provide a business intelligence and marketing automation software services. We execute hyperlocal advertising campaigns, and that means getting people into brick-and-mortar stores to a large degree. There's a lot of different components of this. One component is computational advertising, serving ads on the web. That's what I personally do. There's a lot of other stuff going on. If you're not familiar with this particular field, when you go online, you look at a page, and there's an ad up there. That slot was auctioned off in a real-time bidding auction, and that takes place very fast, on the order of 100 milliseconds or less. A lot of different people compete. They decide, do I want to bid on this slot, and how much do I want to bid? So the decision about whether we want to bid on an ad slot or not is based on a lot of different things. For example, what website are we looking at? Where on the website? The top, the middle, the bottom, whatever. What's the content of the, how does that relate to what we're trying to sell? Who are we serving it to? Does this person, whatever we know about them, demographics or whatever, look like someone who might buy our product? Also time. What time of day are we serving? Is this a likely time for someone to buy our ad? So there's a lot of different things that happen, and you can imagine there's a lot of data science and machine learning that goes on behind the scenes. So obviously classifiers and discriminative models and predictive algorithms. You're trying to predict clicks, you're trying to predict events, someone downloading a coupon or whatever. Sparse models. There's many, many different things that might predict whether or not you're going to buy something. And not all those things are relevant, so you have to do feature selection. We do a lot of natural language processing and topic modeling to understand the content of a web page. We do network modeling because web pages are connected to each other and there's information in that we might want to use. We do things that might not traditionally be considered machine learning, such as control theory and real-time control, because we have very complicated bidding algorithms. We have to kind of keep them in check. We do causality stuff because you need to know whether what you did had any effect. And we also do Bayesian methods. And frankly, if you open a machine learning textbook and you point, you've probably done something there. So with respect to Bayesian methods, we're interested in those because we're very interested in algorithms that can update in real time, or at least pseudo-real time, because the online ad-based ecosystem which we serve ads in is constantly changing, both to the sites coming and going, or some new event happening in the world. And so we need things that will adapt. And Bayesian methods have this nice thing that you have prior belief, and then data comes in, and you update them, and you get the posterior. You can do this recursively. So I'm going to talk about Bayesian stuff in the context of logistic regression. If you don't know what this is, it's one of the most commonly used classifiers or probability models for binary data, 0 and 1, so click, no click, or whatever. But beyond click prediction, it's used in a lot of different places. It's used in modeling disease, epidemiology. It's used back in my days as a computational neuroscientist. We use it for modeling neural spike trains, which are action potentials, binary 0 and 1. It's used for genomics, if you have a lot of genes on a chip, predicting which ones are actually influential on whether you express a certain protein or whatever they do. A lot of other stuff as well. Very briefly, why wouldn't you use linear regression for binary data? Well, linear regression is y equals x times feature, so if x is your feature matrix, linear would be y equals x times w, your parameters, and the red line is a linear regression, or sort of one. And you can see the problem with it is if you're trying to predict probabilities, linear regression shoots off to plus or minus infinity. So that's no good. You need a probability between 0 and 1. So logistic regression, you pass that x through w through a sigmoid. There's no pointer. Anyway, that's that equation up there. And it keeps the blue curve between 0 and 1. That's kind of the simplest way to look at it. There's lots more complicated ways to look at logistic regression in terms of exponential families and whatnot. But I'm not going to talk about that. Because it's so common, it's very easy to do. You can do it in scikit-learn. It takes 3 or 4 lines. And you can do it in a lot of other places as well. And one of the nice things about it, although it's a very simple model, is you're solving a convex optimization problem, which essentially means the functional, the energy that you're trying to maximize or minimize if you flip it upside down, is essentially a big ball. So you don't get stuck in local minimum and you kind of wander your way down. And there's a lot of different algorithms for doing this. So W is, you'd maximize this log of this P of D. D would be your data, conditioned on W, which is your parameter, so you're maximizing the log likelihood. Now, one of the problems with maximizing the likelihood only of something just dependent on your data is that it's severely prone to overfitting. So if you don't have enough data, you're going to overfit your training data and your model will not generalize to test data. So often what people do is they regularize. So they add this blue term here, which is a regularization term. This particular regularization is called L2 regularization because you're adding the L2 norm. So basically the sum of all your fitted parameters squared. And this keeps things in check, okay? Now, this is, there are other ways as well, L1, which is sparsity and so on. But I'm just going to mention L2 for now. Now, this is great, but what this effectively does is this assumes, if you look at it from a Bayesian perspective, where you're updating it, it assumes a prior belief that your parameters are 0, okay? So basically, it assumes a Gaussian prior, where you assume that the prior distribution of all your parameters is peaked at 0, and then there's some normal distribution around there. So I'm going to show you that L2 regularization is actually a special case of Bayesian logistic regression to then move into what we're actually going to do. So if you don't know Bayes' rule means that your probability of your parameters conditioned on your data, that's your posterior, is proportional to the probability of your data conditioned on your parameters, which is your likelihood multiplied by the your prior probability of your parameters. These are all probability distributions. And what we usually do is you assume some simple prior, which is Gaussian here. So basically your prior distribution is an exponential of a quadratic form. W naught is your prior mean. The sigma naught is the prior covariance matrix on your Gaussian. And if you work this through and you take the log of this, what you usually do is when you solve for this with a prior, you maximize maximum a posteriori estimation, where you're finding the parameter that maximizes the posterior probability. And we usually do this in log space simply because the probabilities are really small. And when you do this, you see that the second term there now becomes a quadratic form. Now, if we then go and set both W sub naught, which is the prior mean, to 0, and sigma sub naught to an identity matrix, what you have is you recover the L2 regularized regression. Okay, so everything just drops out, and now we're back to L2. So L2 regularization is Bayes when your prior means are 0 and you have an identity matrix for your prior covariant matrix. And that's great if we don't know anything about what we think our parameters should be. It's kind of a null assumption. But what if we think we do know something and we don't want our prior means to be 0? Well, despite the fact that it's a very simple thing, we found when we were poking around with this that scikit-learn doesn't do this, and we couldn't find a nice little Python package that does. But we might want to do this. So scikit-learn wraps it linear, and that just does L1 and L2 regularization for the most part. It has some other solvers also. But we may have some prior belief about what our parameters should be. We might want to have non-zero means. And one of the reasons we might want to do this is if we're doing recursive updating a model. We might want to start, we might want to fit our model, we might want to do some prediction, but now we've got new data, so we might want to update, and then update again, and then update again. And if you always are having, each time you fit a model, have a prior mean of 0, you're throwing away everything that happened before. We don't want to do this. Now, unfortunately, one of the reasons that most packages, actually I don't know, but I hypothesize that most packages don't have this, is there's not a nice closed form solution when you're doing logistic regression for Bayesian. There is for linear regression, it's all Gaussian, and Gaussian is propagated through. But the problem is that the log posterior, the posterior distribution is not a Gaussian in this form. So we started with a prior that was a Gaussian, but the posterior is not. You can do this by Markov chain Monte Carlo, or you can cheat and approximate, and people do this all the time. So it's very common to say, well, my posterior isn't Gaussian, but it might be close enough. So if that blue curve up there is the true posterior distribution, you might say, well, it might be a Gaussian. And if you have enough data, its central limit variant often is. So you approximate it with a Gaussian, and it turns there's several different ways to do this, but one particularly simple way is called the Laplace approximation, and you essentially tailor expand your log posterior to second order. And it turns out that gives you a Gaussian, and it turns out that the posterior mean is now your maximum a posteriori estimate, and your posterior variance, or covariate matrix, is the inverse of the Hessian of the log posterior. Now, why is this cool? Well, because it's a convex optimization problem, and often we use Hessians when we do convex optimization. So you get this now for free, and now you can easily do your Bayesian logistic regression under this assumption. This is actually pretty standard stuff. You can find it in Murphy's machine learning or Chris Bishop's pattern recognition if you want to read up on it. It's all in there. A lot of other places you can find it too. Or you can just download the code. So we put this on our GitHub page. You can also install it with pip install Bayes Logistic. It's BSD3+, so use it wherever you want with no warranty or anything implied. Now, I want to now walk in through just a couple examples of how to use this code, just show you what you can do with it. It's not that complicated. You can import it, and I'm going to import it as BDL, and if you print out all the functions, you get a bunch of different functions. But there's really only 4 you need to care about. The rest are helper functions. The first one that you care about, the most important, is this fit underscore Bayes Logistic. That's the one that actually performs Bayesian logistic regression fitting. There are 2 functions, logistic prob and Bayes logistic prob, which allow you to, which are just like the first one is just a sigmoid probability function, logistic probability. The second one uses all the information in the distribution of the posterior, so not just the mean of your posterior parameters, but also the uncertainty, the width of the Gaussian posterior, and that moderates the probability a little bit. It uses a probit approximation to the sigmoid. Again, this is all in Murphy and Bishop. The final one is kind of interesting. This is a function that calculates p-values or significant values on your fitted parameters, and you can use this to perform variable selection. And I'm going to go through the first one and the fourth one. The other 2 are very simple. There's also an IPython notebook, and it's got a demo file in it. It actually goes through everything in gory detail, and it shows you how to use everything. So it should be very straightforward. Okay. So let's talk a little bit about fitting. So we have full-on doc strings. It describes everything. This is the one for fit Bayes Logistic. There are 4 required inputs that you need to care about. So Y here, I don't know how well you can see, but Y, you basically need an input of a binary response vector, which I'm calling Y. You need a covariate matrix X or feature matrix. You also, that's what you need for standard logistic regression. You also need a vector of prior means and on your parameters and a matrix of prior Hessians, a prior Hessian matrix. So this is all that you need, and the mean and the variance matrix are the sufficient statistics of the Gaussian, so that's all that you need to fully describe the prior. Outputs, it will spit out an array of, or vector rather, of posterior fitted parameters, and it will spit out the posterior Hessian. So now you have everything you need to then do the next step to iteratively update. So I'm going to show a couple examples, one with fake data and one with real data from MaxPoint. So I'm going to make some toy data, and what it is isn't actually too important, but I just wanted to briefly say what I'm using here so that the results don't look too funny. I'm going to make a correlated feature matrix out of some sine waves, so X in the middle is my feature matrix. The first column is just a bias column of all ones, so that's like the mean probability. Then I have a couple columns of uncorrelated sine waves, and then a couple columns of correlated sine waves. And I actually truncated this matrix. What I'm using for the simulation is actually 11-dimensional feature vector, chosen for no particular reason. If you look at the correlation, the plot on the right, that's the correlation coefficient matrix of X. And so what you can see is that the matrix, except on the diagonal, the matrix is mostly completely uncorrelated, except for that block down the bottom. So this is one, I chose this because I wanted to have something that had off-diagonal elements, the Hessian, basically. I'm going to randomly choose a true parameter matrix. So this is just some random 11-dimensional vector. The first one where I set the bias to -1, just so I got probabilities that came out nice. And because I now have an X and I have a W, I can now calculate, I can now simulate binary response, a binary response vector Y. And all you do is you pass the X and the Y through this logistic prob function or whatever your sigmoid is, get for each data point, get what the probability that there's an event is there, randomly flip a coin and get a 0 or 1. So now you have a binary response vector of 0 and 1s, which we're calling Y, and a feature matrix X. And now we're all set up, except that we don't have any priors yet. Now, let's pretend we don't know anything. So, for your prior parameters, you can choose whatever you want. For your prior Hessian, there's some restrictions in that your Hessian has to be positive definite. One matrix that I know that is positive definite is the identity matrix. So to start, I'm going to do L2. I'm going to choose, so the blue curve on the left there is the true parameters. The black is, I'm going to say, well, okay, my prior means are 0, and my prior Hessian is diagonal, and I just picked some regularization term. I don't even remember what it was. It doesn't really matter, because we're going to do Bayesian updating. So this is actually L2. We can now define a prior, and we define a mean and prior Hessian, and now we can fit it. And this is all that it takes. It's really just W posterior is, H posterior is fit phase logistic, Y, X, prior mean, prior Hessian. And here I used 100 points to update. Okay, it's doing better, it's doing okay, but we could do better. And now is where the power of doing the Bayesian approach comes in. Because this was our posterior mean and our posterior Hessian, but we can now say, well, let's say that's our new prior, and let's do some Bayesian updating. And now, so we update with 100 more points, and we get a better fit. Make it a new prior, update again with 200 more points, and we get an even better fit. And we do it again, and we can keep going and keep going and keep going. And the point here is that because we're not throwing any information away, we're always doing a little bit better. And that's some of the power of Bayes. Now, I should point out that if things change, if your feature matrix was not stationary, then it would then adapt, because your prior would then be, so if like the parameter vector changed midway through your data, now you would have this prior, but it would be wrong. But it would slowly adapt to the new thing as you go along. And that's really useful in a problem like click prediction, because the fact of the matter is that nothing is constant in, well, anywhere really, and certainly not online. So in the click prediction problem or event prediction, you know, it could be clicks, it could be download. You want to know if someone's downloading a coupon, it could be whatever. You want to predict these events. These events are going to be very rare. Across the industry, like you might find numbers quoted on the order of 1 over 1,000 for click-through rates. That's just kind of an industry-wide average. I'm not saying that's anybody's or ours click-through rate. So you want to use all, the point is it's rare. You want to use all the information that you have. So the features, and you have some information about what it might be. So the features might be information quantified about who it is that you're looking at, what's on the website, time of day. But you have this binary response prediction problem. Now, the standard approach would be to fit, take some data, fit a classifier, and then use it to predict some new data. And that's great. The problem is, and this is a problem not just if you're doing logistic regression, but if you're doing any model, random forest, boosted trees, whatever you're doing, is that in general, when you run one of these campaigns, you're running it over many days. So you don't just sell them something on one day, you sell it over some extended period of time. And one thing one could do is you could fit a new model each day and then predict it, or some fraction of that or multiple of a day. But if you do this, the performance is going to stay roughly the same over your entire campaign. You're never going to get any better. Well, maybe. I don't know. This is is actually an example of this. This is real data from our system. It's some event that we're predicting based on some features. And what you're showing is this is the red line is a median predictiveness, I'm calling it, over, I guess it looks like 19 days. And this is a median over 30 different campaigns that we're running. And the shaded bit is 50% confidence bands on that median, so 25 to 75% confidence. The y-axis is actually, this is a measure of predictiveness based on the log likelihood of what you're trying to predict, where it's the increase over the over mean rate model. So that's what this actually is. And there's some normalization in there too. It's not really too important because I'm going to use it for comparison purposes. And what you can see is that you don't really do any better in this very contrived example. It looks like it goes up, but it's well within, what you would expect by random chance. So what you could do instead is you could take a Bayesian approach. So on day 0, year 1, you have some data. You assume a prior mean and Hessian. You fit it, and then you predict. Now, the next day, you take that, you fit it to new data, and you predict, and then you update and update and update as you're going along. And if you do this, the result looks something more like this. So now we've used a Bayesian approach for this online event prediction. And you can see that we improve over time. And it's because we're not throwing any information away. Now, I don't really know. I actually didn't look at the fitted parameters when I did this. So I don't know if they're constant or if they're convergent mean or they change. But it doesn't matter because you're constantly updating. And if what your parameters should be changes, it will follow it within some lag. So that's the main feature of this package. You can do Bayesian logistic regression fitting. There's a few other features I just want to talk about very briefly. I just want to point out that you can use a diagonal Hessian. So you don't have to use the full Hessian matrix if you have large problems. You can use diagonal. You can also do, what I meant by there is that if you put in H, if it's a matrix, it will assume you have the full Hessian. If it's a vector, it'll assume it's diagonal. It does a whole bunch of input checking in case you screwed up your dimensions. Another nice feature is suppose that you trust some of your data more than you trust other points. And then what you have, you might want to weight different data points differently. Now in scikit-learn, you can weight different classes differently. It often does a sampling with replacement of points. But you can also go straight into the log likelihood and put a weight in there. And that's what we did here too. So you can actually arbitrary weight individual points. There's a bunch of different solvers as well. This thing actually wraps SciPy optimize. You can do something else if you want. The equations are the same. And right now we just have in there Newton conjugate gradient, BFGS if you don't want to use a Hessian, LBFGSB if you want to have something that's a bounded solution. And you could go into the code and modify it and use whatever you want if you care to. But there's one other thing I want to talk about in detail, and that's how to do sparse variable selection. Now, here's the point. Usually when we think about sparse variable selection, we use L1 regularization, or we use the lasso, or we use something similar to that. And lasso is a difficult problem to solve. The fact that the penalization term doesn't have a nice parabolic shape. It's got kind of a V, so it's got discontinuity in it. So standard gradient-based solvers have some issues. You have to use the interior point methods and things like that. But you can also, if you're taking a Bayesian approach, you can make an approximation and you can calculate a significance level on all your fitted parameters. And the reason you can do this is you don't just have a point estimate, you have an approximation of the distribution. So up here, if I have a Gaussian, and that Gaussian is centered about 0, then probably that is not a very significant parameter fit. If it's shifted over and from 0 and the distribution is not overlapping 0, then it's probably significant. And so what you can do is you can just use the Wald statistic and calculate a p-value, okay? This is freshman statistics. And you can do this, and it actually works surprisingly well. So I just want to show a little example of this. There are references in the code if you want to read up on this. You can also just use the function get p-values. You can see the references are at the bottom. And what you do is if you have your posterior fit, you put in the posterior means, you put in the posterior Hessian, and it will spit out a vector of p-values, one for each of your fitted parameters. And despite all the problems that we know about p-values, If they're small, they're generally good, and if they're large, they're generally not. So we can use this. Simulation. I made some random data, 200 parameter feature vector, which is going to be sparse. And it's not too important what this data actually is, it's just a little simulation. But if you look up here, so the x-axis is the 200 parameters, the y-axis is their values, and the red is actually the true parameter vector that I used to generate data, fake data. Now, if you fit as we normally would, you get the blue line, and that's obviously terrible. This is severely overfit. But what you can do is if you calculate the p-values, you just calculate the wall statistic, you see that many of them are very large, and many of them are very small. And that dotted line at the bottom of the graph is 0.05. So if you take all those, and you throw every other parameter away, and now you refit using just those parameters, you recover the sparse feature matrix. Is this as good as the lasso? No, the lasso is the optimum thing, as far as I know anyway. But this is fast, and it often works surprisingly well. So I'm going to wrap up with a summary, very briefly the points we're trying to get across. So scikit-learn didn't have Bayesian logistic regression as Bayesian linear regression, but it didn't to our knowledge have it. And we decided to code this up and put it out there for anyone to use. The point is that you can do this with a Laplace posterior approximation. It's very simple. It provides more than just the map estimate. There are more complicated ways as well. Obviously, mean field methods are full on MCMC. But this is a simple, quick way. And this package-based logistic allows you to do recursive Bayesian updating. It allows multiple solvers. It will perform variable selection for sparse models. It has a bunch of nice little things. And there's a full-on IPython demo notebook which you can play with. And that's basically the end of the talk. I hope it was informative. The final thing I want to say is, like many people, we are hiring. And we are hiring data scientists and data engineers and other people. We're hiring here in Boston, we're hiring here in Raleigh, and our headquarters in Raleigh, North Carolina, and our engineering headquarters in Austin, Texas. If you have any interest in that, come talk to me or to some of our fine recruiters, Ashley and Matt, at the table downstairs. Thank you.